These are the notes for partial derivatives. So what we're going to look at now are partial derivatives. So yeah, long time coming, but here they are. So there are a lot of different ways. You know, when we're taking partial derivatives of multivariate functions, things could get a little fun. So let's make a few notes here, and then we'll start getting into what partial derivatives are and whatnot. But so let's consider this. Let's consider, so as you already know, there are multivariate functions, you know, that show up a lot in the real world. We looked at like the ideal gas law before, you know, spring break. You probably forgot about that, but maybe you didn't. But you know, what if I consider this function? Volume equals 1/3 pi times r squared h. So what if I wanted, right? So this is a multivariate function, right? This is a function. I could write this as v is a function of radius and height, right? I could write it like that, right? So, you know, what if I had the question, what if I wanted to hold one of these variables constant and see how much the other variable changed, right? So when you take derivatives of single variable functions, you know, you just find the rate of change of that one variable. All right, that's straightforward enough. But what if I want to find the rate of change of just one of these variables? So question. Let's say I hold, so for a constant r, let's say I hold r constant. I could hold h constant, but for just this case, let's say I hold r constant. How fast does h, or I'm sorry, not h, v, my camera's being really stupid today. How fast does v change with h? So I'm trying to find, you know, if I hold r constant, I want to find how much the volume changes with respect to height instead. That's what I meant to, yeah, this is v. So this right here is a description. So this is basically describing a partial derivative. And what I'm talking about here is, you know, if I hold r constant, so if what is the derivative of v with respect to h? That's what I'm asking. But since this is a multivariate function, right, this is a two-variable function, this notation isn't very accurate because, you know, This expression right here, I'm holding a variable constant, and then I'm saying what's the other variable's rate of change? Well, this is very convoluted. It's it's not very clear. So what we do to illustrate this is instead of writing a dv/dh, we can describe this whole phrase with a different description of a derivative. We could write it as fancy d, fancy dh. So it kind of looks like a like I said, a fancy d. But what this right here is talking about, this right here is the partial derivative of volume with respect to height. And I know I'm getting a little ahead of myself right now, but this right here is basically the description of this. So in general, so before I actually get to that notation though, I'm going to do the limit definition of what it represents. So the partial derivative of f with respect to, let's say we're going to do it with x, is df dx, right? This is fancy fancy dx. It's a little different than, the accustomed derivative that you're looking at. So the definition of this is the limit as h approaches 0. And don't worry about the technical definition. I'm just showing you for completion purposes, but other than that, you probably won't see it again. That's going to be equal to the limit. So what this means is we're taking the derivative of f with respect to x, but we're holding the other variables constant. So I'm going to have the limit as h approaches 0. So because x is moving, I'm going to have some change in x, right? But y is going to remain constant, right? Ordinarily, this would just be f at x plus h minus f of x over h. But now I'm considering two coordinates. Minus the function all over h. So that's the limit definition of the derivative, or the partial derivative with respect to x. And you could do a similar argument for df dy. Just swap this argument. So this will be, if it was df dy, this would be x comma y plus h, and everything else is the same. So likewise, I'll just write it down. So in this case, x is held constant, but y is going to change. Right. And, there's really nothing, when it comes to the limit definition of partial derivatives, that's probably all you're going to see, but, I just want you to understand what it represents. We're looking at the rate of change of one variable at a time. Basically, that's what we're doing. Okay. So what this measures, so to summarize this what this is measuring is it measures the rate at which f changes when x changes. And this measures the rate at which f changes as y changes. Or yeah, basically I could say as here as well. So that's what it represents. All right, so I just want you to understand that's the big idea. But when it comes to seeing this, I'm not going to ask you to do the limit definition of the derivative for a multivariate function, because that would not be easy. So notation, and I already talked about this, but I'm going to do it now. Notation for partial derivatives. So just like there's a number of ways you could illustrate a derivative with single variables, you could do it with multivariables as well. So df dx, so the partial derivative of f with respect to x, you could write it as this: f with a subscript of x. That's perfectly fine. So that's one case. Another case is if I have df dy, that means f with a subscript of y as well. Either one of those is perfectly fine. So, a graphical, it's really hard to illustrate this graphically, but I'll try my best. A graphical interpretation of a partial derivative. So if I make the usual coordinate systems, right? X, Y, and Z. Let's say I have some shape, right? I'll make it a what's this called again? A hyperboloid. Let's just say that's my shape. And let's say I'm at, so this is a function, right? Z equals f of x, y. So let's say I'm at some point. Let me get a different color here. So this point, that's point B, right? Let's say I'm at some point on my curve here, right? And I want to find the rate of change at that point on this curve. So basically what I'm having going on here is this point right here is the function. So x is changing, but on y I'm at b. So this is x comma b. That's what that point is right here. X is changing, but I'm at a particular point in the y coordinate, right? So if I want to find the derivative, if I want to find the partial derivative of the function with respect to x, what I'm saying is I'm finding the slope of this line on this surface. So what does this represent? that represents the slope of z equals the function at that point that's what it represents. It's the slope of this function at x equals b. That's what the partial derivative is for this. Partial derivative. So I'm trying to find, just like in single variable calculus, if you take the partial derivative, or I'm sorry, it's single variable calculus, if you take the derivative, right? Well, the derivative is the slope of the tangent line on a curve. But here, it's the slope of the tangent line on a surface. That's it. That's all I'm saying. So this is just the slope of the tangent line of a point on the surface. So I'll say that right here. Of a point on the surface. That's all it is. And when it comes to computing these things, there's really not much complications with it. It's pretty straightforward. The idea behind it is you take the derivative of one variable while holding the other variable constant. That's it. Really not that hard. What does get tricky, however, is when we start looking at higher order derivatives, and that's when it gets fun. Not hard, but just entertaining. Okay. So, to compute partial derivatives, here's what you do. So to find the partial derivative of f with respect to x, what you're doing is you're making y constant and differentiate with respect to x. Right, that's all you're doing. And then similarly, to find the partial derivative of f with respect to y, you're making x constant and differentiating with respect to y. I know I kind of, with respect to too, I know I kind of did some stupid stuff there, but yeah, you get the idea. So that's really the idea, right? Differentiate the function. So here, basically, you're going to use the same rules of differentiation you learned in Calc 1, and you're just holding the other variable constant. So you're treating the other variable like a number, basically. That's all you're doing. That's really it. That's it. So, example. So find partial derivatives of z equals to a function of x and y, which equals x times e to the xy power. So compute the partial derivatives of those functions. Okay, well, this is a function of two variables. So what I'm trying to find is the partial of f. And you could also write this as dz dx and dz dy, or df dx, df dy, doesn't matter, because they're both the same thing. They both represent the same thing. So df dx. So when I'm taking the derivative of this with respect to x, that means y is going to be treated as a number. That's similar to this, right? You know, if I just go to the side, let me put this in like a little thought cloud. That's the same thing as saying, you know, df dx. That means I'm taking the derivative of x, y is being treated as a constant. So I could think of this as like x times e to the 3y, or 5y, or 10y, or whatever. And then from here, you know, oh, I'm sorry, this will be 3. I'm sorry. You know, from here, you know, just use the chain rule, right? And just take the 3 out, so you'll get 9 e to the 3y power. But instead of actually having, you know, a 3 here, it's just going to be x. So you could think of it as like this. So if I let y be constant, right? So how am I going to take the derivative of this? Well, I'm going to use the product rule. High d low plus low d high. So high, okay, times the derivative of low. All right, so y is constant. So this is like e to the 3y, e to the e to the 10y, e to the 20, whatever. So how do you take the derivative of low? Well, you're going to use the chain rule. Basically, you're going to bring y out. So this will be, so high d low, right? All right. This is my high, this is my low. So this is my high times d low. So d low, so this is going to be a constant, so I'm going to bring this out. So this will be y e to the xy. Because what do constants do? They come out. Y is a constant in this case. So high d low plus low d high. So low is just e to the xy times d high. Well, so d high. So well, the derivative of x with respect to x, that's 1. In this case, the partial derivative. I'm actually differentiating with respect to x, so this will be 1. So that right there is the partial derivative of f with respect to x. So you can clean this up and write this as xy e to the xy plus e to the xy. Now right there is the partial derivative with respect to x. But now I want to compute the partial derivative with respect to y. So in this case, I'm differentiating with respect to y, and x is going to be constant. So that was kind of like this. But here, so here I can make x be a number. So if this is like 10 e to the 10y, how would I take the derivative of that? Well, in this case, I'm not going to use the I'm not going to use the product rule here. So this right here, this is like what? If I write it here, so in this case, I'm going to let y be constant. Or I'm sorry, I'm going to let x be constant. Right? Did I mess this up here? Yeah, I think I messed this up. Oh man. I'm so focused on my projector not working that I can't even concentrate. Let's see here. Yeah. So this should have been what? X e to the 10x. Yeah, it should have been something like that. Down here, so I'm taking the derivative of y, so that means x is going to be constant here. So this would be something like 10 e to the 10y. Sorry about that. Sorry about that. So yeah, you can see why we did the product rule here, because we had x times stuff with x. So here, you can see why we went through the product rule. Sorry about that, guys. So that implies we're using the product rule. Right. Now here, this is a constant times a function. So I'm not using the product rule here. Here I'm just taking out this constant. This is just the derivative of, so the derivative of this, you're going to make this what, 100. So the derivative of this would just be 100 e to the 10y power, right? That's what that would be like. So instead of doing that with a number, just treat x like a number. And just, write in terms of x instead. So now, when I take the derivative of this, I'm going to get what? I'm just treating x like a number, right? So x is going to come out, and I'm going to have x squared e to what I have left over, xy. And that's it. That's the partial derivative of each one. So, depending which variable is constant, it could fundamentally change the problem pretty easily. You could see here, by making y constant, we have a product of two x's, so we use the product rule. By making x constant here, we just have a simple bring the constant out, which is what we did. That's it. So changing the variables can really, the partial derivatives can really make this really, change up pretty easily. Okay. Let f of xy be equal to x to the fifth plus blah, 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 blah. Find the partial derivative of x. So find the partial derivative of f with respect to x. So that means we're holding y constant, right? So whenever you see x, you differentiate it normally, but now you're just making y a number. So x to the fifth, well, since this is with respect to x, all right, just do the power rule here, 5x to the fourth. All right. Now y here is a constant, so it's being treated the same way as 3 is. So basically you could cluster, basically they are the same thing. These things are considered the same thing. So now I just do the power rule on the x term. So I'll just make a little note here. They are the same thing here. Basically. So now, if I take the derivative of x cubed, well, that's just 3x squared, right? So I'll have 3x squared times 3 times y squared, which is 9y squared. So I'll write it all out. So, you know, I'll have an x cubed, right? What's the derivative of the x cubed? Well, that's 3x squared, right? And now I have a 3 and a y squared, right? Because they were constant. Plus, I'll worry about cleaning it up later. Same thing here. I'm taking the derivative of x, so they're considered the same thing. So what's the derivative of x? Well, that's just 1. So I'm going to have 3 times 1 times y to the fourth. So now when I rewrite all that, I have 5x to the fourth plus 9x squared y squared plus 3y to the fourth. So that's the partial derivative of f with respect to x. Now you saw this coming, right? With respect to y. Same idea, just you're switching the variables around. So when you take the derivative of this with respect to y, but what is x here now? Now in this case, this is a constant, right? Now this is a constant. Well, what's a constant to the fifth power if you take the derivative of that? That's just going to be 0. That's just going to be 0. So that doesn't even show up. Plus, now here, I'm taking the derivative of this term. These are going to be treated the same thing. So in this case, those two are going to be considered the constant. And now I'm taking the derivative of y squared. Well, what's the derivative of y squared? 2y. So I have 3 times x to the third times the derivative of that is 2y. Plus, now here, since I'm taking the derivative of y, these are going to be considered the constant terms. And the derivative of y to the fourth is just 4y cubed. So I have 3 times x times 4y cubed. So now when I clean that up, I'm going to have, this is going to be 6x cubed y plus 12xy cubed. So those are the partial derivatives of those functions. And you can see how they look very different, obviously. That should go without saying, but so, when you're taking the derivative, the partial derivatives, the idea is to hold the other variable constant. Let me ask you this. find the partial derivative of f with respect to x at 1, 2. And that's easy. Right? That's easy. You can just plug that in, so you're plugging this into the partial derivative function. So plug that in here. So that's 5 times 1 to the 4th plus 9 times 1 squared, 2 squared, plus 3 times 2 to the 4th. So that's just a straight computation. When you go through that, you're going to get 5 plus 36 plus 48, which equals 89. So, to summarize, what does the partial derivative of f with respect to x at 1, 2 represent? What does that represent? That represents the slope of the function So what does this represent? So this is the partial derivative with respect to x. So that means y is being held constant. So the y coordinate is being held constant, but x is changing. So this is the slope of this function at the particular point x equals 1. That's what this represents. So x is changing, but we are at 1. We're finding the slope at 1, but y is always going to be 2. Because this is the partial derivative with respect to x. Okay. Well, so, you kind of got the idea of computing partial derivatives, and, it's really not that complicated. It's just using all the rules you've learned in single variable calculus. You're just holding the other variable constant. So why don't we look at functions with more variables? We only looked at the 2-variable case, but now let's look at the 3-variable case. And then we're going to get to higher order partial derivatives. Because like in Calc 1, you've also looked at, the second derivative and so on. Well, that exists here. But it's really interesting. All right, so note, the same idea applies to computing partial derivatives of functions of more than 2 variables. For example, if I have or given w equals, so w is a function of 3 variables, x, y, z. So if I'm given that function, its partial derivatives are df dx, which you could write as f sub x, df dy, which you could write as f sub y, and since I'm doing 3 variables, it would be df dz. So, you know, for as many variables you have in the function, you're going to take just as many as partial derivatives. You know, there's really nothing too complicated about that, but, you know, I just want you to recognize that, you know, if you have partial derivatives of functions of more than 2 variables, just keep going for as many variables as you have. There's really nothing complicated about that idea. Okay. So, now that we know that, what I want to do now is I want to talk about higher order derivatives. So this is where things get really entertaining in Calc 3. It's not as straightforward as single variable functions. When you take the derivative of a single variate function, you just keep going, right? But here, so if I looked at this one for example, right? So if I take the first partial derivative, right? F of x, f of y, f of z. All right, partial of x, partial of y, partial of z. But instead of, so because I have a multivariate function, I have different permutations for each one of these guys. So what I'm saying is I'm going to have a partial derivative of x, y, and z for this one, x, y, and z for this one, and x, y, and z for this one. So I'm going to have different permutations of partial derivatives for each one of these partial derivatives. I know that seems really convoluted, but hopefully it'll make more sense as I keep going. So basically, what I'm saying is this. So note, suppose, so I'll just keep it simple right now. I'll just look at the two variable case. Suppose z equals f of xy. The second derivative should be the derivatives of the first derivatives. Go figure. So what are the first two derivatives here? All right. So the first derivatives are, all right, df dx and df dy. All right. So now, like I was saying up here in a 3-variable case, but I'm keeping it simple here. So each one of these is going to be differentiated with respect to x and respect to y as well. That would be the second derivative. So the second derivative so this is just going to be two derivatives from that one and two derivatives from that one. So this is going to be differentiated with respect to x and with respect to y. So the way we write that, just extend this idea here. So let me make this look a little bit better. So this is going to branch out into a and b, and this is going to branch out to c and d, and I'll be able to write those out down here. So a is going to look like, well, this is going to be the derivative of this with respect to x. So I'm going to have that. Right? I'm going to have this, and that's going to be differentiated with respect to x. And that's what I have here. This is not 2x, that's fancy d. So this is going to be differentiated with respect to x. Now, I just keep going. So b, the function, the partial derivative with respect to x, right? That's the first derivative. That's going to be differentiated with respect to y. All right? And then I do it for this one. So the derivative of, the partial derivative with respect to y. Each one of those are going to be differentiated by x and y. So this is going to be df dx, or d dx, I'm sorry, and this will be d dy. So basically, the first derivatives are, that's easy. The second derivative, you're differentiating this with respect to x and y, and then this one with respect to x and y. So you get a total of 4 second order partial derivatives. So notationally, I'll just say notation-wise. So the way we write this, we could write this as, if I want to use, writing this is really convoluted. So what I could do is I could rewrite this with the subscript notation, like, for example, like I write this as this, and I write this as that, right? Well, this right here is f sub x, but I have another x on top of it, outside of it. So it's f sub double x. So the way I write this, basically, I start from the inside, I work my way out. So the first one is df with respect to x, and then the outer one is fy. So what I'm doing here is I'm taking the derivative, or partial derivative with respect to x first, and then I take the partial derivative with respect to y second. Start from the inside and work your way out. Just kind of like PEMDAS, basically. So in this one, this is the partial derivative with respect to y first, right? So this one is the partial derivative with respect to y first. So this will be f sub y, and then you take the partial derivative with respect to x. This one, well, since they're both y, take the partial derivative with respect to y, so that's f sub y, and then y again. So here are my second order partial derivatives. So basically, notation-wise, we could write this as f sub xx, f sub xy, f sub yx, and f sub yy. Those are the second order partial derivatives. Those are 4 second order partials. So when you compute these, just basically, when you're computing, start from the inside, work your way out. So, you know, in this one, you do this one first, and then that second, and so on. You know, it seems really, you know, it seems really, I don't want to say confusing, but it seems really obtuse. But it's really not that bad. It's really not. Let's look at an example. Compute the second well, I don't want to say order, sorry. Compute the second partial derivatives. Of z equals x squared minus 3xy plus y to the fourth. So when you're doing this, compute the second partial derivatives. So what you want to do is you want to, obviously you want to compute the first derivative first. So do the first partial derivatives. So the first derivative, so that's the partial of z with respect to x and partial of z with respect to y. So what's the partial of z with respect to x? Well, so you got to get good at doing these things, just like you would do with single variable calculus. So take the derivative with respect to x, every other variable has remained constant. So derivative of x squared is going to be 2x. The other variables are constant, so the derivative of x is 1. So I have 3 times 1 times y, so I have 3y. or, well, I should say minus 3y. And then, well, this is a constant to the fourth. The derivative of a constant is 0. So that's the partial with respect to x. What's the partial with respect to y? Constant squared, that's 0. Don't care about it. All right, partial with y is 1. So I have negative 3 times 1 times x. So I'll have negative 3x. And then the derivative of y with respect to y is 4y to the third. So that would be plus 4y cubed. All right, so those are the first derivatives. That wasn't hard. But now the second derivatives, this isn't hard either. It's just a little longer. So now I got to differentiate this one with respect to x and y, and then differentiate this one with respect to x and y. So basically, remember, you're going to start from the inside and work your way out. So you're going to tack these second derivatives on the outside of the subscript notation. So that one with respect to x first, and then with respect to y. And then this one will be, right, so that's the, and then this one with respect to x, and then that one with respect to y. So then I'll have all my partial derivatives, my second partial derivatives. So just go through them. So what's the derivative of this with respect to x? Well, so this will be 2, right? And, well, this is just a constant, this whole thing. Negative 3 is a constant, and y is a constant when x is being differentiated. So this is the derivative of a constant, which is 0. So this is just 2. Now with respect to y, this is a constant in this case, right? This is the derivative. So the derivative of y is 1, so 1 times negative 3 is negative 3. Okay? So now, this one, so I'm taking the derivative of this one with respect to x, right? So the derivative of this with respect to x, well, that's going to be 1. So I'm going to have negative 3 times 1, which is negative 3. And then the derivative of this with respect to x, well, this is just going to be a constant, right? So that's going to be 0. So I have negative 3. And then I have the derivative of this with respect to y. This is a constant, right? This is a constant. So that's going to be 0. And then the derivative of this with y, so that's going to be the power rule. So this will be 12y squared. So those are my partial derivatives. I want you to notice something here. Now, that wasn't hard. That was pretty, it was pretty straightforward. But I want you to notice something here. And this is pretty important. Look at these two guys right here. What do you notice about these two? What do you notice about them? They're equal, aren't they? Yeah, they're equal. That's not a coincidence. Your textbook describes this as a theorem, and I'll make a note of it. I'll make a note of it. These two partial derivatives right here. So if you look here, this is the partial derivative xy. This is the partial derivative yx. xy, yx. Those are called mixed partials because they contain the same variables. They're flipped around, or in other words, they're mixed. Sorry. So I'll just say right here, so note, notice how the, quote, mixed partials, what do I mean by mixed partials? I mean z xy and z partial yx are the same. And this is a theorem. So if I go to the next page, this is a theorem. And what this theorem is called is there are multiple variations of it. This is called the mixed derivative theorem. Or it's the mixed derivative theorem, or your textbook calls it Clairaut's theorem. I'll spell it Clairaut's theorem. I prefer the term mixed derivative theorem. I don't know about you, but I'm just giving you that information. And all this theorem is basically saying is that if the functions are nice, what do I mean by nice? What I mean is they're continuous, then the mixed partials will be equal. That's all it says. So I'll just, I'll make a note of that here. So if x comma y and its partial derivatives f comma x, I'm sorry, f sub x partial of y, and then partial of xy and partial of yx. So if all of its partial derivatives, right, if all of its partial derivatives, if the original function and its partial derivatives are defined and continuous, at a point A, B, or, at some domain, then I could say that their partial derivatives are equal. Their mixed partials are equal. So these two, for example, will be equal because they're the mixed partials. They're the mixed partials because they're equal variables, x, y, yx. So then I could say the partial of xy at AB is equal to the partial of yx at AB. That right there is Clairaut's theorem, or the mixed derivative theorem. So basically, if the functions are, so what do I mean? They're defined and continuous. Basically, they're nice. Spoiler alert, in this class we're only going to really look at nice functions, but just as long as you realize in the real world usually nice functions don't apply. But so when it comes to computing partial derivatives, we might end up computing 4 of them, but we're only really going to get 3 because this one and this one will be unique, but since these two are the same, there's only going to be 3 unique partial derivatives. And the same thing is true if I go and, if I have x, y, z, same thing. But if I have another variable, I'm going to have more mixed partials to consider. But basically, that's all I'm saying. So, let's look at one last example here. Compute the second partial derivatives of w, which is a function of x, y, and z, and that equals 2xy plus 3y over z. Okay. Beautiful. So now, if I want to do this, well, I got to take the first derivatives. So I have to take the partial with respect to x, y, and z, and then I have to take the derivatives of x, y, and z of each one of those. So it seems like I'm computing 9 partial derivatives. Lovely. You can see why this gets really fun. So the first derivatives are going to be, so I'll just use subnotation to make this easier. So this will be the partial with respect to x, partial with respect to y, and the partial with respect to z. Alright, so now I'll go through them. So that means y and z are going to be considered constants here. So, all right, well, the derivative of x here is 1, so I'm going to have 2y. And since this is a constant over, no, these are constants, right? So I don't care about that, so that's just at 2y. All right, 3wy. So that'll be 2x. And well, this is going to be a constant, so this is like 3 over, so this is like a fraction times y, right? So this will be like, what's the derivative of y? Well, it's going to be 1. So this will be plus 3 over z, right? And then the partial with respect to x, well, I'm sorry, with respect to z. Camera's being goofy again. So this is a constant. I don't care about that. Well, so I'm taking a derivative with respect to z. So, okay. So what I want to do here is I want to think of it as like, this is some number over z to the, over z, right? So this is like, 2 over x. And if I rewrite that as 2 to the negative first power and then use the power rule. So I'm thinking of it like that, right? So when I do that, so I'm just going to bring the power out, right? So I'm going to rewrite this as 3y times z to the first. And now take the power rule. So I'm going to have negative 3y times z to the negative second, which I could just write as negative 3y over z to the second. All right. I'm just thinking this one is that, right? Okay, those are the first derivatives. That's easy. So now what I want to do is I want to take the second derivatives. Alright, so now I'm going to have the derivative of this one with respect to x, with respect to y, and with respect to z. So this one with respect to x, with respect to y, with respect to z. So I have that one with respect to x, with respect to y, and with respect to z. All right. Then I have this one that's going to be with respect to x, with respect to y, and with respect to z. And then this one's going to be with respect to x, respect to y, and with respect to z. So yeah, I have all these partial derivatives to compute. Great. So, you know, some of these could be really easily. I mean, if you look here, what's the partial derivative of this one with respect to x? That's easy. 0. All right. Partial derivative of that with respect to y. Well, derivative of y is 1, so I'm going to have 2, right? Okay. And with respect to z, well, there's no z here, so it's going to be 0. That was easy. So, you know, using Clairaut's theorem, you know, or the mixed derivative theorem, you know, this function is defined. You know, the only place where it wouldn't be defined is at z when z is 0, right? But provided it's not 0, I could use the mixed derivative theorem and say that, all right, well, the mixed partials are going to be the same. So I could say that y, you know, the partial with respect to x and y, I could say yx, right, which is right here, that could also be 2. And, you know, you could either go through it yourself, or you could use the mixed derivative theorem or Clairaut's theorem to see that. So what's the partial derivative of y with respect to x? Well, that's going to be 2, right? Because the derivative of 2x is 2. This is a constant, so that's 0. 2 plus 0 is 2. Or using the mixed derivative theorem, yx, xy, they're the same. All right. What's the derivative partial with y and y? Well, there's no y's in here, so that's going to be 0. And the partial derivative of y with respect to z? Well, I do have a z in here, so I'm going to rewrite this as what? 3 times z to the negative. This is going to be 0, so this will be 3 times z to the negative first. All right? That'll be like 3 times z to the negative first, which when you take the derivative of that, it'll just be negative 3 z to the negative 2, which is going to be negative 3 over z squared. All right, keep going. And again, zx, xz. That could be 0, or you could just do it yourself, right? Go through this. There is no x's in here, so it's going to be 0. zy. Well, so I'm going to take the derivative of y. That's the same thing as yz, right? So if we go through that, take the derivative of this with respect to y. Well, the derivative of y is 1, so I'm going to have negative 3 times 1 times times z squared. So that's going to be negative 3 over z squared, which is exactly what I have. Hey, negative 3 over z squared. And that, they're the same because of the mixed derivative theorem. And then the partial of z with respect to z. Well, I just, y is going to be a constant, right? So this will be what? So just to do the power rule in the z term. So negative 2 times negative 3 is 6. And since y is a constant, it's going to stay there. And then z to the negative third, which is just yz, or I'm sorry, 6y over z cubed. So those are the second order, those are the second derivatives, but I really only have 6 because some of them are equal to each other, right? I really only have 6. Right, so here's 1. So I'll just underline the unique ones that I have, right? Those are unique. These are the same. These are the same. Here's a unique one. So those are the same. Those are the same, right? And those are the same. And finally, these are the same. So I have 1, 2, 3, 4, 5, 6. So I really only have 6 partial derivatives. But, that's how you would do it. So there are 6 unique second order partials. Again, you could go through it, but provided that the functions are nice, you can see that Clairaut's theorem is very useful because it could save a lot of tedium when you're doing these things. But, that's really the basic idea when it comes to these things. So in the next video, what I'll look at is we're going to look at the chain rule, which sounds daunting, but it really you know, I don't think it's personally that bad, but, you know, we'll look at the chain rule for computing partial derivatives. Like if I have functions of, you know, if I have a function, but then x and y are also functions of other variables. So we'll look at how we do that when we look at the chain rule for multivariate functions.